want to give you another example of finding volume using the washer and the shell method, and I want to compare those two methods in this video. So we're just going to do an example. We're going to use both the shell and the washer method to find the volume of the region bounded by y equals x squared and y equals 2x if it's rotated about the line y equals 4. So I'm going to start, as always, by drawing a picture. Y equals x squared is my standard parabola. Vertex at the origin opens up. Y equals 2x is a line that goes through the origin and has a slope of 2, so up 2 over 1. I want to figure out where these two functions intersect. That's going to help me both with my picture and with finding my bounds of integration. So I'm going to take the two functions, set them equal to each other. X squared equals 2x. I set one side equal to 0 by subtracting the 2x. And then we can factor out an x. If we pull out an x, we're left with an x squared minus, we pull out an x, we're left with an x minus 2. We can set both of those factors equal to 0, and we get x equals 0, x equals 2. So these two curves intersect at x equals 0 and at x equals 2. That would be at the origin, 0, 0, and at the point 2, 4. If I take x equals 2 and I plug it into either of these functions, I get a y value of 4. So my intersection points are 0, 0, 2, 4. Now I'm going to sketch in that line y equals 4. That's our axis of rotation. So we're taking this object and we're rotating it about that line, y equals 4, to get our three-dimensional solid, or solid of revolution. So we're going to find the volume using two different methods, and hopefully we get the same answer. We should get the same answer. So we're going to start with the washer method. When you use the washer or the disk method, your slices, or rectangles, have to be perpendicular to that axis of rotation. So if I create slices that are perpendicular to the line y equals 4, that would be vertical slices. When I take these rectangles and I rotate them about that line y equals 4, I'm going to get washers, or circles, donuts, circles with holes in them. Because I made my slices vertically, the width of each of these slices is a delta x, a change in x, or a dx. So using the washer method, the integral I'm going to set up is going to be pi times big R squared minus little r squared, outer radius and little radius. And I'm going to be working in terms of x. Everything is going to be in terms of x. So my radius, my distance to the outside of the object, is this line that I'm highlighting right now. It's drawn in blue. To find the length of this line, I'm going to take the top, which is always y equals 4, minus the bottom, which comes from my parabola. So my big R is 4 minus x squared. Top, y equals 4, bottom, y equals x squared. Little r would be the distance to the inside of this object. That's going to be y equals 4, that's where we're starting, always y equals 4, down to the line, which is y equals 2x. So little r would be 4 minus 2x, top minus bottom. My integral is pi times the quantity 4 minus x squared squared minus 4 minus 2x squared. And my bounds of integration are going to be x values as well. I'm working in terms of x. This object starts at x equals 0 and stops at x equals 2. So my bounds go from 0 to 2. To solve this integral, I would FOIL out the quantity squared, combine like terms, and then integrate. So 4 minus x squared squared would be 16 minus 8x squared plus x to the 4th. And then 4 minus 2x squared is going to be 16 minus 16x plus 4x squared. I'm going to subtract those two quantities. The 16s cancel out. And then we have 8x squared minus a 4x squared. That gives me 12x squared, plus x to the 4th, and then minus the minus 16x gives me plus 16x. Finally, this is something we can integrate. Antiderivative of negative 12x squared is negative 12x cubed over 3. Antiderivative of x to the 4th would be x to the 5th over 5. And then antiderivative of 16x is 16x squared over 2. I'm going to simplify those antiderivatives a little bit. So I've got pi negative 4x to the 3rd plus x to the 3rd over 5 plus 8x squared. And then I plug in my bounds of integration. I'll plug in 2, I'll plug in 0, and subtract them. And this ended up simplifying down to 32 pi over 5. So that's the volume of this object. Now I want to compare this method to the shell method. So let's do the exact same problem, but let's set it up with the shell method. And we should get the exact same answer since we're finding the same quantity. We're trying to find volume. So when you use the shell method, your slices or your rectangles have to be parallel to your axis of rotation. Our axis of rotation is the line y = 4. So our slices or rectangles have to be horizontal. If we're slicing horizontally, the width of each of those rectangles or each of those slices is a dy. That tells me I have to set up this entire integral in terms of y. I'm going to be working in terms of y. Using the shell method, the thing that we're going to integrate is 2 pi r times h. But my r and h have to be functions of y. So we'll start with r. Radius would be the distance to that axis of rotation. So this little line segment I've drawn is my r, my radius, distance from my slice to my axis of rotation. The top there is always y = 4. And then the bottom of that little purple line segment is wherever my y value is, wherever I am on this picture. So my radius is going to be 4 minus y. Radius is 4 minus y. The height of my cylinders is the length of these little rectangles. So I'll do right minus left to get that length. So that would be the parabola minus the line. But we're working in terms of y, so I need to take both of those equations and solve them for y. My parabola, y = x squared, becomes x = square root of y. The line, y = 2x, becomes x = y over 2. So then the height of my rectangles, or the length of that little blue line segment that I'm highlighting right now, would be the right side, which is x = square root of y. So square root of y minus the left side, which is x = y over 2. So square root of y minus y over 2. Putting this into my integral, I'm going to be integrating 2 pi 4 minus y times square root of y minus y over 2. Because I'm working in terms of y, my bounds of integration are also going to be y values. So this object starts at y = 0 and stops at y = 4. So my bounds are from 0 to 4. To do this integration, we'll have to multiply this out. I'm going to go ahead and change that square root of y into a y to the 1/2. And then using FOIL, my first would be 4y to the 1/2. Outer, 4 times negative a half is negative 2, so negative 2y. Inner is going to be negative y to the 3/2. I added the exponents to multiply. That was a y to the 1 times y to the half. 1 plus a half is 3/2, so y to the 3/2. And then last, minus y times 1/2 y, it's a minus 1/2 y, would be a plus 1/2 y squared. All right, integrating, we get first term 4y to the 3/2 over 3/2 minus 2y squared over 2 minus y to the 5/2 over 5/2 plus 1/2 y to the 3rd over 3. And then I'll simplify that antiderivative a little bit because I know dividing by a fraction is the same as multiplying by the reciprocal. So we still have that constant, that 2 pi. And then I've got 4 times 2/3, that's 8/3, y to the 3/2. Next term, the 2's cancel out, so just minus y squared. Next term, dividing by 5/2 is the same as multiplying by 2/5, so minus 2/5 y to the 5/2. Last term, we can take the 1/2 times the 1/3, that gives us a 6th y to the 3rd. All right, finally we can plug in those bounds of integration. So I'm going to plug in 4, and then I'm going to plug in 0. I get 0 when I plug in 0, and subtract those values. And so I did a bunch of arithmetic. Feel free to use your calculator to help you with something like this. And I ended up getting 2 pi times 16 over 5. And if I multiply, that becomes 32 pi over 5. And notice that was the exact same answer we got in the previous video. I hope this helps clear some things up when it comes to both of these volume methods. Please let me know if you have any questions on this video.